Thank you very much, Valeria, for your introduction. And before starting, let me say that I'm very grateful to the program committee for this opportunity to present my work here at this conference. And I also wish to thank the program committee for their amazing work in organizing this conference. So what I'm going to present is a joint work with some colleagues from Pavia, from Vienna, and from Zurich. And more precisely, it will be on non-standard finite element methods for wave propagation problems. So before saying what a non-standard is, I would like to make it precise what I mean by standard. And if you have attended Alfio Quarteroni's talk this morning, probably you already know it. So I consider that I have a partial differential equation. So let me say Lu equals to F in a domain omega with boundary conditions. And so first of all, we want to write that in a variational formulation. So we multiply by test functions and we integrate by parts. Then the finite element method, so the standard finite element method, is a Galerkin method, which consists basically in taking finite dimensional subspaces of the functional space V and restricting the variational formulation to this finite dimensional subspace. So that will be the standard Galerkin method, and the standard finite element method consists in using piecewise polynomial functions defined on a mesh of the domain, a mesh which usually is made by simplices or by bricks. And since we want to have conformity, so we want usually the space V is a space of H1 functions. So we want these piecewise polynomial functions to be continuous across the boundary of the elements of my partition. So what is again standard when we approximate time-dependent problems is that we start by a finite element approximation in space only, and then we do a time stepping, so we solve the ODE system that arises from the finite element discretization in space, and we do time stepping to evolve the solution in time. So wave propagation problems are challenging for this standard setting. So they have highly oscillatory solutions, so which means that a very high resolution is required, that usually they're posed in complex materials, so you can have different wave velocities in different subdomains, so the resolution which is required may be different in different subdomains. And once you have corner singularities or solution singularities, you might want to use very fine meshes close to these singularities. And then when you combine the space discretization and the time discretization, you have that when you have very small spatial elements in some parts of the domain, then to avoid instabilities, you have to take very small time steps everywhere. So what I'm going to talk about, so the non-standard approximation I'm going to talk about, break this standard paradigm of finite elements in several directions. So for instance, instead of doing a variational formulation in space and then time stepping, I start with a space-time variational formulation. Then instead of using standard meshes, we try to use problem-oriented meshes. So for wave problems in particular, I will use sub-characteristic meshes of the full space-time domain. And then instead of using the Galerkin setting, I will use the discontinuous Galerkin setting, which means that I don't require that my piecewise polynomial space are globally continuous. So we also have to modify the bilinear form and the right-hand side to accommodate this discontinuity. And then in the end, instead of taking standard polynomial functions, I will try also to use problem-adapted basis functions, so related to the operator that we want to discretize. So just very briefly, why the space-time setting? So in the space-time settings is kind of a monolithic discretization using, say, polynomials in space and time, it's easy to write a higher order method by simply increasing the polynomial degree. So we don't have to combine two different methods like a space method and the time stepping. And then by suitably choosing the space-time variational formulation, one can achieve stability under a local CFL condition only. So basically, the smallest elements in space do not affect the choice of the time step everywhere in the domain. And then the numerical solution in a space-time setting is available at all times in the interval of interest and not only on the discrete times. The drawback of that is the high complexity. In fact, if you have a problem in d space dimensions plus time, you have to solve a d+1 dimensional problem. So what I'm going to present now, after introducing the model problem, I'm going to describe the space-time discontinuous Galerkin discretization and its properties, and then I will present two ways to reduce the complexity of the final problem to that of a d-dimensional problem. So from the complexity in d+1 dimensions to the complexity in d dimensions, and these are the references this is going to be based on. So here I just collected some general references, but what I want to point out is that early works on space-time finite elements are actually pretty old. So they date back to the end of the 80s and the beginning of the 90s of the last century. And the other thing that I want to point out is that most of these space-time methods are based on the discontinuous Galerkin setting. So this is actually my model problem. So as a model problem, I consider the acoustic wave problem, but I write it as a first order system. So I define a capital Q as a space-time domain. So omega is space and 0t is time. I'm assuming that I have a wave velocity c, which is piecewise constant in my domain. And then I have a source term and initial conditions. And I write the problem as a first order system in two unknowns, a scalar valued unknown b and a vector valued unknown sigma. So these are my two equations, my two first order equations, and then I have initial conditions, and for simplicity, I take zero Dirichlet boundary conditions. So to see the relation between this problem and the second order wave equation, it's enough to think that v is the time derivative of a function, say capital U, and sigma is minus the gradient of U. So by using these two definitions, basically you rewrite the system as the standard second order wave equation. So I want to use space-time finite elements, which means that I need to start from a space-time variational formulation. And so I have here, I copied here my two equations, my two first order equations for my system. And also in the following, for brevity, I say that I read that as the wave operator applied to V and sigma is equal to F0. So this wave operator takes two functions, gives me back to, again, a scalar valued function and a vector valued function. And basically, and is a first order operator. So I derive the space-time variational formulation by taking the two equations, multiply by test functions, and this is what I obtain, and then I integrate by parts. So if I integrate by parts, so since this is a first order problem, so you see that the full wave operator is applied to the test functions, and then you have some terms and the boundary arising from the integration by parts. So now, if I want to introduce a discontinuous Galerkin finite element method, I cannot do a global space-time variational formulation because in the end, my basis functions will be discontinuous. And so basically, I will write this variational formulation element by element. So here I have again my two equations. So first of all, I will introduce a mesh of the space and time. And then I multiply by test functions and I integrate by parts, element by element. And then I will have also inter-element boundary terms arising from this integration by parts. And then I discretize the functions in discontinuous piecewise polynomial spaces. So since in this way the elements do not speak to each other, in order to do the communication among two adjacent elements, I will replace the inter-element traces of my functions by the so-called numerical fluxes, which have to take into account also what happens in the neighboring element. So they have basically to establish the communication between the elements that I broke by taking discontinuous functions. And this will be the idea. So in the next slides, I will present the assumptions that I make on the meshes, the assumptions that I make on the numerical fluxes, and the assumptions that I need to make on the approximation spaces. So for the meshes, I assume that I don't choose my meshes randomly or in a standard way, but I'm assuming that the interior faces of my meshes are either space-like or time-like. Time-like means that they can only be parallel to time, and space-like means, space-like means that they have to, so these faces are obliquous, but they have to be below the characteristic lines that are determined by my local wave velocity. So here I depicted the mesh. So here is like a Cartesian type mesh. In this case, we have time-like faces, the vertical faces, and here all the space-like faces are horizontal. Here in the upper part, I only have a space-like faces, and they are obliquous and below the characteristic lines. So for the fluxes, so we observe that across space-like faces, the information should travel from lower time to higher time. And so we will define upwind fluxes. Whereas on time-like faces, when we have time-like faces like a vertical one, there is no directionality. And so the fluxes that I'm going to use are standard fluxes that are used also for elliptic problems, which means are linear combination of averages and jumps of the traces. Whereas what is important for space-like faces, I always transmit what comes from lower time to higher time. As far as the spaces are concerned, so I recall the definition of the wave operator, and my assumption is the following. So if I have a pair of piecewise polynomial functions which are in my discrete space, then also their image through the wave operator has to be in this discrete space. But this is not very difficult to realize, while since the wave operator is a first order operator, by applying it, if you have polynomials, you decrease the polynomial degree, not globally, but maybe only in one variable, and so you stay inside the space. So for instance, if you have standard polynomials in space and time, this assumption is satisfied, but this is also satisfied if you have tensor product in time polynomials. And even if you have, this is trivial, if you have the so-called Trefts polynomials, which means polynomials which are also in the kernel of the wave operator. Because this is trivial, because the wave operator applied to this Trefts polynomial will be 0, and 0 is contained in any space. So with this setting, it is quite easy to prove well-posedness of the discontinuous Galerkin formulation with the assumptions that I gave. And everything is based on a property, on a very important property that I call coercivity in semi-norm. So I define this semi-norm as something that only contains jumps of my solution of my discrete spaces across inter-element boundaries, so across the mesh interfaces or traces. And this is only a semi-norm. This is not a full norm because it doesn't. So if you have that this is 0, you don't have that, you have 0 functions. So you just have that the jumps are 0 and the traces are 0. And what is valid is, so here is in a simple case, but this can be generalized quite easily, that you have that if you take test functions equal to trial function, you have that your bilinear form defining your method is equal to the squared of this DG semi-norm. This is not a norm, this is only a semi-norm, but this structure is similar to the structure of an elliptic problem. And this is what is going to be very useful for the analysis, because you can partly treat this hyperbolic problem, so the discretization of this hyperbolic problem, like in the elliptic setting. So I don't enter that, but then I can say that in an almost straightforward way, you also have a control of the error at discrete times, in this case, without imposing any condition on the size of the elements in time with respect to the size of the elements in space. So we have unconditional well-posedness and unconditional error estimates, where we say that the error is bounded by the projection error of the solution into the discrete space. And this is valid with no condition linking H, T, and Hx. So you can take thin elements, thin and high elements, and this still holds. Of course, the approximation is not very accurate, but still we have this a priori estimate. So now I would like to exploit this setting and try to reduce the computational cost in two ways, as I said at the beginning. The first one makes use of the so-called Trefts basis functions, and the second one makes use of the so-called combination formula. So for the first one, we have to restrict to the case where f, the right-hand side of the function of the problem, is equal to 0. So the problem is driven by initial and boundary conditions. And here I recall the definition of the wave operator. So this is my first order wave operator. So we have two components because I write it as a system, as a first order system. So here I define what I mean by Trefts spaces. So continuous Trefts spaces are simply, so here I define already these spaces on a mesh. So I'm assuming that K is a mesh element, is one element in my mesh, and I define a local continuous Trefts space as a space of functions which are in the kernel of the wave operator. So this is an infinite dimensional space. And then I take copies of this local space element by element, I put them together without continuity constraints, and I define my global continuous Trefts space. Continuous, I mean infinite dimensional, because actually it's made of these continuous functions. So now if I want to have Trefts finite elements, I have to take finite dimensional subspaces. So I simply take finite dimensional subspaces of the local space, and then I simply put them one near to the other, and I build up my global space. So the global space will be a finite dimensional space made of piecewise discontinuous functions, such that within this each element, I'm in the kernel of the wave operator. So what is a good news here is that if I look at this operator within each element, I see that the wave of all the terms appearing in the wave operator are of the same order, of the same, so are derivatives of the same order. So everything is first order. And since I'm assuming that the wave velocity c is piecewise constant, assuming that my mesh is aligned with the possible discontinuities of c, so c is also constant within each element. So one can easily see that if you take functions which are, so infinite dimensional functions which are in the kernel of the wave operator, and you take Taylor polynomials of these functions, so you see that you cut your Taylor expansion, and you see that when you take a Taylor polynomial, you remain in the kernel of the wave operator. So from an approximation point of view, this means that if you have a function in the kernel of the wave operator, it's enough to approximate it, so you can choose, basically, you can choose Trefts spaces made of polynomial functions, and you can define them in such a way that with this subspace, so instead of taking the full P space, you just take the subspace of the polynomials of degree P that are in the kernel of the operator, and you have that you can reach the same approximation properties as for the full polynomial space. So when you have functions in the kernel of the wave operator, you can reach the same accuracy as in the full space, but just saying in a subspace. And in the subspace, if you count the number of, so if you count the dimension of this Trefts subspace, so you see that if you are in space-time dimension, so d in space plus 1 in time, while, so these are in the right column, so these are the dimensions of the full polynomial spaces. So then if you restrict to Trefts polynomial spaces, so you see that the number of degrees of freedom will be of the order of a polynomial degree to the power d. Instead, the full space-time polynomials, full polynomial space will have dimension order of a polynomial degree to the d plus 1. So you can increase, so you can improve the accuracy. Sorry, you can maintain the accuracy, but with less degrees of freedom. So you can reduce the number of degrees of freedom without destroying accuracy. So this is basically what I wanted to show here. So here I increase the polynomial degree and I plot the error. So blue is Trefts, orange is full polynomials. So here we see that we have the same type of convergence, even if the accuracy here is better for full polynomials because the space is larger. But then if you plot, instead of the polynomial degree here, you plot the number of degrees of freedom that you need. So you see that with the blue, with the Trefts, you can have the same accuracy with much less degrees of freedom. So this is exactly what you can prove theoretically. So for the analysis, things are quite easy. So in the Trefts spaces, the DG semi-norm is actually a norm, and the analysis basically in this case goes like for elliptic problems. So things are quite easy, and then by duality argument you can also prove a global convergence in the space-time domain in a volume norm. So here I want to quickly show that the Trefts approach combines very well with the so-called tent pitching meshes. So tent pitching is a mesh construction technique that is introduced for hyperbolic problems that consists in building the mesh of the space-time domain by advancing the front in time. And the front in time is advanced by stacking on top of each other some objects that are tent-shaped. And the height of the pole of each tent is chosen so that the causality constraint of the PD is respected. So for instance, in the case of the wave propagation problem, if c is the wave velocity, and assuming that is constant here, and then this red dashed line is the line of slope 1 over c. So if you have a tent, you want the dipole is such that the tent is below this characteristic. So this makes the PDE solvable within each tent because the domain of dependence of each point of each tent is within the tent. So basically, you can evolve the solution that you have at the bottom up to the top without looking outside this tent. So this is how things go. So assume that at the beginning, your front is basically times 0. Then you pitch a tent. And this is your first tent. And now you have to evolve the solution from the bottom up to the top. And if you use the Treff's approach, since you don't have volume terms in your formulation, you can just restrict basically your formulation to the tent. And you see that you can find the solution. So the solution at the bottom is known. So the beginning is just the initial condition. And you can evolve the solution up to the top just by inverting a small matrix that only considers the degrees of freedom within this tent. So then the front is advanced, and so you can do the same for the neighboring tent. And what is important is that you can solve these two tents in parallel. So if you have all the tents on the same level can be solved in parallel. And so that's what is advantageous from a computational point of view. And then once you have advanced the front, then you continue until your domain is filled up and you have the solution at final time. And this is just to depict the tents also in the 2D setting. So now what so maybe I skip some numerical tests where I just wanted to show that things behave as expected. And I just want to show that even if you have a solution, so a wave problem with a solution displaying a corner singularity, so this is a pretty high singularity, then even with, so you can do tent pitching and be able to recover full order of convergence just by starting with a space mesh at the time 0, which is refined close to the, suitably refined close to the corner. Then you apply your tent pitching algorithm, and then you see, for instance, with polynomials degree equal to 3, so you expect to have a convergence for smooth solutions, a convergence of order 4 in L2 norm. And this is what you see that is correctly captured also with this tent pitching plus Treff's method. So the blue one will be what happens if you start with a uniform mesh. So you cannot improve, you cannot have the full approximation power of your polynomials because the solution is too singular, so is not smooth enough to have convergence of order 3. So with the standard, say, elliptic tricks, you can safely recover full convergence also in case of corner singularities for the wave equation. So now, building up, so again, focusing on the corner singularities, I would like to present a second way to reduce the number of degrees of freedom without reducing the accuracy in a space-time approximation of the wave problem. So again, I will start exactly from the same discontinuous Galerkin method that I presented, but now I don't use Treff's polynomials, I simply use the full polynomials. And then I will reduce the number of degrees of freedom with another technique. So here I restrict to the case of 2 space dimensions because there the regularity theory is well known. So for instance, what we know in 2D is that the singularities of the solution of the wave equation are only conical singularities that are located either at the domain corner or at a corner between two different elements. So assuming that I have different elements filling my domain, and each, different materials filling my domain, and each material occupies a subregion, then I collect all the corners of my partition into these subdomains, in which I'm assuming that the wave velocity is piecewise constant. And so basically what I have is that the solutions to the wave equation do not belong to the standard Hilbert spaces, but they belong to weighted Hilbert spaces, where the weights are basically functions that measure the distance, so products of functions that measure the distance from corners elevated to a given exponent between 0 and 1. So what is important is that these spaces are spaces, so for instance, in the lowest case, these weighted spaces, H11 delta, is not even contained in H1. And if I consider the solution V sigma of my wave problem written as a first order system, so for V there is no much problem, but for sigma, so sigma will be the gradient of the solution of the standard wave equation. So for this sigma, we have that this is not even in H1. So the regularity is low, and this of course affects the global approximation properties of any method. So what I'm going to do now is I consider now, so now I don't use the Trefts spaces, and I concentrate on the case where I take meshes, space-time meshes, which are tensor products of space meshes that can be, for instance, triangular meshes, times time intervals in a partition into intervals of 0t. So assuming that I have meshes of space and I have a mesh of time, then I consider my space-time mesh of my space-time domain as a tensor product of elements in space times the time interval. So on this, I can apply my theory, and I end up with an estimate of the error of the method by the L2 projection error. So here things are a bit more complicated if I want to consider solutions with realistic regularity, because the sigma is very singular, close to corner points. And so in the elements that are close to corners, the traces of sigma on the faces are not even in L2, so they are only L1, but one can also deal with this case. So here we have seen that we have lack of smoothness of our solutions, and this lack of smoothness gives a loss in the accuracy of the L2 projection of the solution. So which means that if I take uniform meshes, I have a very poor convergence in the end, because my L2 projection on our uniform mesh is not able to give high order approximation for singular solutions. But then the singularities again are very similar to the singularities of elliptic problems. And so one can basically reduce the size of the elements close to the corners in order to restore the largest possible rates. So what is lost in the exponent has to be gained in the basis, so in the size of the elements. So basically, what we are going to take is that whenever you are close to a corner, the size of your elements close to the corner should be small enough, depending on the Sobolev regularity of the solution close to the corner, and depending on the polynomial approximation that we are going to use. So basically here I depicted the case of here a uniform mesh, and here a graded mesh if I use a polynomial degree equal to 1, and here a graded mesh if I want to use a polynomial degree 2. So you see that here you have to to do basically the grading of the meshes is harder. So, which means that the elements close to the corner must be smaller, because here you want to reach second order of convergence, whereas here first order of convergence would have been enough. So in this case, so assuming that we have these space-time meshes, one can prove that if we assume that in each element, the wave velocity times the size of the element in space, in time, is almost equal to the size of the element in space, then you see that you can get optimal order of convergence. So with these graded meshes, we can prove that we can restore the full order of convergence. So everything here is nice from a theoretical point of view, but from a practical point of view, we can see that this is reached with a number of degrees of freedom, so with a dimension of the discrete space equal to the order of the mesh size to the power -3, which means the same complexity, not as a two-dimensional problem, but as a 2 + 1 dimensional problem. We are in space and time, so we are in dimension 2 + 1. So the question is, can we obtain the same convergence rates, but only with order of h to the power -2 degrees of freedom, which means instead of the complexity of a 2 + 1 dimensional problem, with the complexity for a two-dimensional problem? So the answer is yes. And this is achieved by using the so-called combination formula. So we have seen that this assumption that links time, the size of the elements in time and the size of the elements in space is necessary to obtain the highest convergence rates. But the stability, the existence and weakness of solutions and stability of the DG formulation was achieved with no condition on HT. So this condition is necessary only for the accuracy, not for the stability. So apparently this means that if we violate this constraint, we have not very accurate solutions, but the solutions we have are still meaningful, or better, they still contain some meaningful information. And so we can use them, we can use combinations of them in order to reduce the number of degrees of freedom and obtain the same accuracy. And this is how this is done. So this is the so-called combination formula. So I plot here on the x-axis the number of refinements of my meshes in space. So assume that here I have the very fine mesh in space, and here coarser, 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 and even coarser in space. On the y-axis, I put the levels of refinement in time. So basically here, I have the finest mesh in time, and here I have coarser and coarser meshes in time. I want the accuracy of the red dot, so of my mesh, which is very fine both in space and in time. So for computing that solution, I have a complexity like a d+1, so in this case 2 + 1 dimensional problem. So instead of computing this solution, I can take a linear combination of the solutions located at the black and blue dots. So basically here, this solution is obtained with a mesh which is very fine in space, but very coarse in time. And here, that's the same meaning here, and the similar meaning for the blue ones. So instead of computing this red solution in the fine space and time mesh, I compute these intermediate solutions, and then I add together what I obtain corresponding to the black cases, and I subtract what I obtained in the blue cases. So I assemble what I call the sparse, what people call the sparse solution. So the full solution will be the red one that I don't compute. And then I assemble this sparse solution. So what can be seen is that this sparse solution has the same accuracy as the full solution. But if I count the number of degrees of freedom that I need to assemble each of these problems and I add them together, I see that the number of degrees of freedom that I need to assemble the sparse solution is of the order of h to the power minus 2, which means instead of h to the power minus 3, that will be the cost, the number of degrees of freedom to obtain the red one. So basically, one can obtain the same accuracy as the full solution with a reduction, like a meaningful reduction of the dimension. And so basically it's like the same cost of a one time step on the finest spatial mesh. So I have reduced the complexity as I wanted. So I think that, so here again, I just wanted to show that things go exactly as we expected. And with this, I wish to thank you very much for your attention.